Hello everyone, I am Dipanshi from BSc Chemistry Honors 3rd year. Today I am here giving the presentation on the topic carbohydrates. Introduction. One of the most important classes of biomolecules is carbohydrates. These include compounds like sugars, starches, glycogen, cellulose, dextrins and gums. Although they are widely distributed both in animal and plant kingdom, yet they are obtained mainly from plants. They are formed in plants by a process known as photosynthesis and make up about 70% of the solid plant material. CO2 plus H2O gives CH2O plus XO2 carbohydrate. Carbohydrates play a vital role in our daily life. They provide us with three basic necessities of life: food, clothing, and shelter. Food in the form of starch, clothing, cotton, Limon and rayon are essentially cellulose, shelter, wood in making houses and furniture in almost cellulose. Classical definition. The name carbohydrate, meaning hydrate of carbon, was originally given to a class of compound containing only carbon, hydrogen, and oxygen. The hydrogen and oxygen being present in the same ratio as in water, these compounds could therefore be represented by general formula C6H2OY. Limitations of the old definition. The above definition could not survive long due to the following reason. A number of compounds such as rannose, C6H12O5, deoxyribose, C5H10O4 are known, which are carbohydrate by their chemical behavior but cannot be represented as hydrates of carbon. These are the other substances like formaldehyde, HCHO, CH2O, and acetic acid, CH3COOH, CH2, C2H2O2, which do not behave like carbohydrate but can be represented by the general formula CXH2OY. Carbon is not known to form hydrates. Modern definition. Carbohydrate are defined as polyhydroxyaldehyde or polyhydroxyketone or substances which give these on hydrolysis and contain at least one chiral carbon atom. It may be noted here that aldehydic and ketonic group and the carbohydrate are not present in such but actually usually exist in combination with one of the hydroxyl group of the molecule in the form of hemiacetal and hemiketal respectively. Classification. Carbohydrates are also known as saccharides. Now we classify depending upon their behavior towards hydrolysis. Monosaccharide. These are the simplest carbohydrate which cannot be hydrolyzed to smaller molecules. Their general formula is CH2N where N is equal to 3 to 8. Oligosaccharides. These are the carbohydrate which on hydrolysis give 2 to 10 molecule of monosaccharide. Depending upon the number of monosaccharide molecule actually obtained upon hydrolysis, they are further classified as di, tri, tetra. Disaccharide. Carbohydrate which upon hydrolysis give 2 molecule of same or different monosaccharide are called disaccharide. For example, sucrose, maltose, lactose, etc. Their general formula is C12H22O11. Trisaccharide. Carbohydrate which on hydrolysis give 3 molecule of same or different monosaccharide are called trisaccharide. For example, raffinose upon hydrolysis give 1 molecule each of glucose, fructose and galactose. Their general formula is C18H32O16. Tetrasaccharide. Carbohydrate which upon hydrolysis give 4 molecule of the same or different monosaccharide are called tetrasaccharide. For example, Stacchyrose upon hydrolysis give 1 molecule each of glucose and fructose and 2 molecule of galactose. Their general formula is C24H42O21. Polysaccharide. Carbohydrate which upon hydrolysis give a large number of monosaccharide molecules called polysaccharide. The most commonly occurring polysaccharide are starch, cellulose and glycogen. Their general formula is C6H10O5N where N is equal to 100 to 3000. Sugars and non-sugars. Carbohydrates are further classified as sugar and non-sugar. All monosaccharide and oligosaccharide are crystalline solids, soluble in water and sweet in taste. These are collectively called sugar. The polysaccharides, on the other hand, are amorphous solid, insoluble in water and tasteless and thus are called non-sugar. Reducing and non-reducing carbohydrates or sugar. Carbohydrates are also classified as reducing and not reducing sugar. All these carbohydrates which contain aldehydic or ketonic group in hemiacetal or hemiketal form and reduce Cholon reagent and Fehling solution are called reducing carbohydrate or sugar, while other which do not reduce these reagent are called non-reducing carbohydrate or sugar. All monosaccharide, whether aldose or ketose, are reducing sugar. Disaccharides such as sucrose, in which the two monosaccharide units are linked to their reducing center, Aldehydic or ketonic groups are non-reducing, while other in which these groups are in hemiacetal or hemiketal form are reducing sugar. However, all polysaccharides, starch, cellulose, glucose, glycogen, dextrin, etc. are non-reducing carbohydrates. Classification of monosaccharide. As stated above, monosaccharides are the simplest carbohydrate which can not be hydrolyzed to smaller molecules. They contain 3 to 7 carbon atoms. There are about 20 monosaccharides which occur in nature. These are of two types: aldoses. Monosaccharides containing an aldehyde group are called aldose. Since aldehyde group is monovalent, therefore it is always present at the one end of carbon chain at C1. Aldotrioses C3H6O3 C2 CH2OH CHOH glyceraldehyde. Aldotetroses C4H8O4 CH2OH CHOH twice CHO erythrose threose. Aldopentoses C5H10F O5 CH2OH CHOH3 CHO arabinose ribose xylose Lyxose. Aldohexoses C6H12O6 CH2OH CHOH4 CHO. Allose, altrose, glucose, mannose, gulose, iodose, galactose, talose. Ketotrioses C3H6O3 CH2OH CO CH2OH dihydroxyacetone. Ketotetroses C4H8O4 CH2OH CO CHOH erythrolose. Ketopentanose C5H10O5 CH2OH CO CHOH 2 CH2H ribulose. Ketohexoses C6H12O6 fructose, sorbose, decatose, etc. Nomenclature. Monosaccharides are better known by their common names, which is most in cases and in suffix "-ose". For example, ribose, glucose, fructose, etc. The IUPAC names of monosaccharides are seldom used. For example, the simplest aldose containing 3 carbon atom CH2OH, CHOH, CHO, generally known by its common name glyceraldehyde, seldom by its IPAC name 2,3-dihydroxypropanol. Similarly, the simplest ketose is better known by its name dihydroxyacetone and by seldom its IUPAC name 1,3-dihydroxypropane. However, monosaccharide containing more than 4 chiral carbons, aldo, haptose, aldoctose, etc., are named by IUPAC system by uses 2 or more prefixes derived from lowered sugars. The 1 chiral carbon glycerol 2 erythrothrio ribo arabino xylo likes of 4 allo ultro gluco mano gulo ido galacto tallow. The IUPAC name of the sugar is then obtained by giving the prefix denoting the 4 carbon which occur adjacent to C1 in aldoses and C2 in ketosis, preceded by another prefix denoting the next group of chiral carbon up to 4. In IUPAC, deoxy sugar are named by adding 2 prefixes to the name of aldose ketose containing the total number of carbon atoms in the chain. The name begins with the prefix deoxy along with its locand, followed by configurational prefix representing the system of chiral carbon atoms as shown above. Since most of the earlier work on the monosaccharide was carried out by hexoses, glucose, and aldox and fructose, ketones, therefore we will start our study of monosaccharide with these 2 representative compounds. It may, however, be added here that what is true about the glucose is also true about the other aldohexoses, and what is true about fructose is also true about other ketoses. Glucose is the most widely distributed monosaccharide. It occurs free in large quantities in ripe grapes, and that is why it is called grape sugar. It also occurs in honey and most of the other sweet fruits such as mangoes, apples, peaches, pears, etc. It is also present in human blood about 0.1% in the combined state. It occurs in glycoside, disaccharides, and polysaccharides. Preparation of D-glucose. Laboratory preparation. In the laboratory, glucose is prepared by the hydrolysis of sucrose or cane sugar. Sucrose added water then gave glucose and fructose. Manufacture. Sucrose is hydrolysis by heating Sucrose is hydrolyzed by heating with dilute HCl or H2SO4 in 90% alcohol when a mixture of glucose and fructose is obtained. Glucose, being almost insoluble in alcohol, separate out on cooling, while fructose remains in the solution. On a commercial scale, glucose is prepared by the hydrolysis of starch with hot dilute mineral acids. The chief source of the starch are rice, maize, and potatoes. Starch plus H2O gives glucose. After hydrolysis, the mixture is neutralized with the chalk CaCO3 and filtered. The filtrate is decolorized with animal charcoal and concentrated under reduced pressure when glucose crystallizes out. Physical properties of glucose. Glucose is crystalline white solid with melting point 419 Kelvin. It is highly soluble in water but sparingly soluble in alcohol and insoluble in ether. It is optically active and is dextrorotatory and hence the name dextrose. It is about 3/4 as sweet as sucrose. Table sugar. Chemical properties. D-glucose is a typical monosaccharide. It gives the reaction of both the aldehydic and alcoholic groups. In order to discuss these reactions, glucose may be simply represented as an open chain pentahydroxyaldehyde as shown below. Some important reactions of glucose are discussed below. Reaction of aldehyde group. Glucose gives the usual reaction of aldehydes, however, it does not respond to the Schiff reagent test and also does not form addition compound with a saturated solution of sodium bisulfate. Reaction with hydrogen cyanide. Glucose forms a cyanohydrin with hydrogen cyanide. CH2H, CHOH4, CHO plus HCN, CH2H, CHOH4, CHOHCN, glucose cyanohydrin. Reaction with hydroxylamine. With hydroxylamine, glucose gives glucose oxime. Glucose NH2OH, glucose oxime H2O. Reaction with phenylhydrazine. Glucose react with 1 mole of phenylhydrazine to form glucose phenylhydrazone. Glucose plus H2N NHC6H5 CH2OH CHOH4 CH double bond and NHC6H5 plus H2 osazone formation. However, if excess of phenylhydrazine is used, the reaction proceeds further to yield a crystalline product called osazone, which contains 2 phenylhydrazine residues per molecule of glucose, while the third molecule of the reagent is converted into aniline and ammonia. Glucose is converted into glucazone. It may be pointed out there that osazone formation is not only a characteristic reaction of reducing carbohydrate but is also given by alpha hydroxyaldehyde and alpha hydroxyketone is general. Further, during osazone formation, the stereochemistry about C2 chiral carbon of aldose is destroyed without affecting the configuration of the rest of the molecule. Fischer mechanism. Who first prepared osazone explained the mechanism of its formation. The first mole reacts in a usual manner expected of an aldehyde. The second mole oxidizes the secondary alcohol group to the ketonic and the third mole react with the keto group thus generated to form the osazone as shown below. Limitations of Fischer mechanism. The above mechanism suffer from the following effects. It does not explain why phenylhydrazine, which is a strong reducing agent, acts as oxidizing agent. And the second step of the above mechanism. It does not explain why only the first 2 carbon atoms are involved in osazone formation, while the remaining hydroxyl group not oxidized react further with phenylhydrazine. Modern mechanism. To overcome these objections, we Gann proposed an alternative mechanism involving amide rearrangement. The phenylhydrazone first formed undergoes tautomerism to form a hydrogen bond in 6-membered intermediate. The intermediate subsequently loses a molecule of aniline to form an aminoketone. The aminoketone then reacts further with 2 molecules of C6H5NH and H2, one at the CO group and other at C double bond NH to give the final osazone. Glucose hydrogen bond in intermediate glucazone. The mechanism is supported by the observation why phenylhydrazone prepared by N15 called with phenylhydrazine treated with ordinary phenylhydrazine unlabeled osazine is formed with the elimination of labeled ammonia. This mechanism also does not explain why reactions stop after the addition of 2 phenylhydrazine residues. This has been explained on the basis that osazone is stabilized. It may be noted that osazone formation is a general reaction of all monosaccharide and hydroxyaldehyde and alpha hydroxyketone. An important point about the oxazone formation is that during its formation, configuration at C1 and C2 is destroyed, evidently diastereomer monosaccharide, which differs from the glucose only in the configuration as C2 should give the same oxazone. For example, D-mannose, which differs from D-glucose only in the configuration which gives the same oxazone. In general, any pair of the epimer which differ in the configuration at C2 give the same oxazone. Oxazone are well defined, bright yellow crystalline solid having different shape. Therefore, same oxazone are identification of monosaccharide and reducing disaccharide reduction. Glucose is readily reduced catalytically or by sodium mercury amalgam and water to form hexahydric alcohol called glucitol or sorbitol. Glucose is changed into sorbitol. However, in reduction with HI in the presence of red peak, it gives a mixture of anhexane and iodohexane, glucose into anhexane to iodohexane. Oxidation. Mild oxidizing agents such as bromine would oxidize glucose to a monocarboxylic acid called gluconic acid. Glucose into gluconic acid, Br2H2O. Strong oxidizing agents such as nitric acid oxidize glucose to a dicarboxylic acid called glucaric acid or saccharic acid. The second carboxylic acid being formed by the oxidation of first alcoholic group. Thank you.